Okay, next speaker is Qimiao Si, who I know did most of the work for this conference because I'm also
thank you, Matt. So the price of having an in-person workshop during the pandemic time is that you end up hearing some local people like myself. So anyway, but the flip side is that I'm very happy to be part of this session, joining the discussions we just had. So this is a Weyl Kondo semimetal. You already heard in the first talk of the session by Silka Pasha. I want to give some introduction, but also really focus on the design of correlation-driven electronic topology. So it's a bit of a bold claim, and I will explain carefully what I mean by that. But in the meantime, let me acknowledge some of the collaborators. So let me, in particular, recognize who is a graduate student at Rice on the postdoc job market. A lot of great things. Lei Chen, so graduate student, Chetan Sete, a postdoc here. This work started as part of the thesis work of Sarah Gruffy, and you already heard from Silka's talk that the theoretical work and the Vienna, the experimental work from Vienna have gone quite hand in hand. So it's been a pleasure to interact with her and her group. We've had, especially the design part, we've had quite a bit of interaction with Jen Cano, who's here in the audience, and also the ab initio aspect in connection with the symmetry with my Wigneri, and we also had some collaboration with Stefan Kirsch. So here's the outline. I'll talk about the Weyl Kondo semimetal. I'll talk about the design, and I'll report some initial work on gapless electronic topology without free electron counterpart. So I'm not entirely sure I can get through the third part, but so at the risk of that, I thought I would give some introduction for two purposes. One is that part of the workshop is to form some dialogues, and explaining where we came from might help for that cause. And the other is that in some sense, it not only gives some context of where we came from for this line of work, but also where we are headed. So consider a standard interacting model of electrons. You have some band dispersion, E sub over E versus K, and multi-band in the systems we are talking about, and some genetic interactions. So historically, we think about such systems in terms of the perturbation theory of U over W, U being the interaction strength, W being the bandwidth, and a variety of ways from Hachi-Fock all the way upwards. But for the purpose of my talk, the point is that we use the electrons as the building blocks for the physics in the context here, the topology, but also for correlation physics as the building block for low energy physics. So what happens when interactions become comparable to the bandwidth, or even goes beyond that? One of the things that can happen is that the interactions produce effective degrees freedom. Some of them are local degrees freedoms, such as spin and orbitals, to go along with the conduction electrons, the phonons, the very natural building blocks. And that combination is going to play a very important role for the kind of things we're talking about in this session. So this is about heavy fermion systems. I'm going to focus on heavy fermion metals, or at least gapless states. And but even so, the F electrons, for practical purposes, for low energy physics, acts as localized things, and that's going to be the starting point. So for the bulk of my talk, it's going to be the spin degrees freedom. towards the end, touch upon the orbital degrees freedom, how that can change the physics. So we have spins coupled with the conduction electrons. And that is reflected in this model that you've seen several times. You have the local moments of the electrons, which form the quantum magnetism part of the physics. You have the conduction electrons, and the symmetry allows interactions between the two species. And that's the exchange Kondo exchange interaction, which typically is anti-ferromagnetic for reasons. In essence, that's what Phil Anderson told us since a long time ago. And if it's anti-ferromagnetic Kondo interaction, energetically it pays to form Kondo singlet, which is the Kondo state that we've heard quite extensively earlier in the session. Now, a Kondo singlet, you can picture it as the local moment spin, the F electron spin, and the conduction electrons are locked together. Or put in this way, you have a moment and spin, and the triplet combination of the particles and the holes of the conduction electrons, and they form a bound state. And so just like we learned that if we have Cooper pairs, we can break the Cooper pairs to get the Bogoliubov-Digen's quasi-particles. If we have a bound state like this in a ground state, we can consider the excitations of the system by breaking up such a bound objects. And one of the things that emerge is that you can have free electrons as part of the excitations, but also this composite object, this composite fermion, which is called many different names, Kondo resonance, etc. But it's an object that plays a very important role because it means that the electron physics and the spin physics get very much coupled together. So where we came from, sort of this kind of system has been studied for many years. Over the past 20 years or so, it's been the playground to gain intuitions about quantum criticality. And one of the things that has happened extensively, theoretically and experimentally, is that these systems can have extensive list of phases and phase transitions. And if the second order zero temperature phase transition, which sharpens the issues, and also forming singularities, which one can isolate, it turns that, and we've learned that quantum criticality can go beyond the Landau framework of the fluctuations of the, for instance, magnetic order, and it could involve the dynamical effect associated with the breakup or breakdown of the Kondo singlets. And if the destruction of the Kondo singlet, you have these composite fermions which go away, and that leads to not only this kind of fix being picked up in the dynamics, such as the neutron scattering, which was the starting point of this kind of work, this line of work, but also gets picked up in the change of Fermi surface from large to small. And so that leads to various quantum properties like the critical exponents in the dynamics and etc. But that's not the kind of this talk. I just want to mention one more thing, that if one starts to talk about not only the Landau order parameters, anti-ferromagnetic versus paramagnetic, also large and small Fermi surfaces involving the participation of these composite fermions or not in the Fermi surface, one ends up with a richer phase diagram, richer set of phases. And this is a global phase diagram that had already been referred to in the first talk by Sergei Pasha. So that leads me to the specific sort of trajectory followed on the theoretically on the Weyl Kondo semi-metal. The initial question was, can we use spin-orbit coupling as a more controlled tuning parameter to go across the phase diagram? And once one start to ask questions like this, also leads to the next layer of question: how is this phase diagram modified by spin-orbit coupling? And that very naturally leads to the interplay between spin-orbit physics and strong correlation physics. And so over the course of today already, we heard about non-interacting topology and also interaction effects. which could come in, for instance, by forming broken symmetry state, magnetic order state, which gives you a handle to control the weakly interacting electronic topology in that kind of background. The focus here is on topological states which are actually driven by strong correlations. So here we have a model for that, and I want to focus on the gapless case. And so the first step, let's set a goal which is concrete and in some way also modest. Is a model whose ground state is topologically trivial without a Kondo coupling and becomes topologically non-trivial in the presence of the Kondo effect. That was how we started to think about this problem. And so we end up with a model which I only discussed very briefly, was already referred to, and Sarah Graffi, who couldn't be here today and much of tomorrow, she'll be talking about the Zeeman field tuning of this Weyl Kondo semi-metal state. So we wanted to have a non-symmetric lattice. So diamond lattice is like the sort of the hydrogen atom version of 3D lattices that gives nodal excitations. And so it's non-symmetric. We can break the inversion symmetry and preserve time reversal symmetry. So lo and behold, within this Kondo lattice model, in the Kondo screen phase, where there's a Kondo singlet in the ground state, and then you have composite fermions in the excitation spectrum. In the case of the diamond lattice, and introducing some with some inversion symmetry breaking term that's incorporated, we end up with the solution for the spectrum, and there's a linear dispersion of the excitations emitting out of these Weyl nodes. And as already referred to, the velocity is much reduced from the non-interacting value. But more importantly is that these are these composite fermions forming bands. So the Kondo effect is driving the formation of these Weyl nodes. And it's a genuinely interacting system, but if they happen at a Fermi energy in this state, they're sharply defined, infinitely long-lived. So we can talk about Weyl nodes. And the filling is such that it pings the Weyl nodes to the Fermi energy. That requires a particular type of filling that we work with. If you go beyond this filling, you're still getting solutions of this kind because the Kondo effect pings these composite fermions to the immediate vicinity of the Fermi energy in any case. So in that sense, this kind of solution is much less to the filling requirement than the purely non-interacting problems. And highly reduced velocity is very important because it can be picked up by the correlated electron community. Entropy is one thing that the correlated electron community thinks quite extensively and most naturally, and it can be probed, as Sirka already talked about. And the other thing is that if the nodes are in the immediate vicinity of the Fermi energy, the Berry curvature distribution is such that in the vicinity of the Fermi surface, it's extremely enhanced, and including some details like with tilting in the potential, one can make it asymmetric, and that's very important for thinking about transport, consequences for transport from this kind of Kondo-driven Weyl state. So that's as much as I want to say about the Weyl Kondo semi-metal. Then I'll turn to the design. And this is a bit of the scary proposition because designing materials is challenging. Designing correlated materials is still more challenging, right? And especially designing non-interacting materials, at least ab initio helps. Designing strongly correlated materials, ab initio does not obviously help us. Or at least it's very difficult. So the idea is that can we bypass difficulty, this inherent difficulty, by using symmetry? And so one could motivate this by thinking several different ways. One way of thinking about is that, well, let's take the CM3 bismuth 4 palladium 3 as the starting point. We have a gapless chlorine topology, but there's only one material. So can we go expand the material space? All right, if we can get one more, that's 100% increase. If we get two more, that's 200% increase in the material space. Another way of saying it is that in non-interacting systems, graphene was recognized as a symmetry enforced nodal state, hosting a symmetry enforced nodal state. One doesn't stop there. It provides a motivation to go far and beyond and sample through the space groups, and that has been a success story leading to a larger, for instance, just topological semimetal database. Can we do the power of that for the correlated systems? So that's two kind of ways of motivating this work. So what is the analog of going from thing to topological semimetal database of non-interacting systems for this kind of strongly correlated systems? So the guiding principle for us is the following. Strong correlations, we know that they do a lot of things, but invariably they produce emerging low energy excitations. And now these emerging low energy excitations, just like non-interacting electrons, they live in the same crystalline environment. So one could picture that the crystalline symmetry will have constraints on these emerging low energy excitations. That's one way of saying it. A more more hazy way of saying it is to say that strong correlations and the space group symmetry might cooperate, just might work together as opposed against each other to produce these kind of correlated topological phases. And in turn, we can use that as a basis to design materials. So, so we want to do for this task, we want to go beyond the hydrogen atom model. We want to go beyond the diamond lattice. And we were led for a number of different reasons that I don't have the time to explain. We were led to consider the square nets, in particular space group 129. And if you break the inversion symmetry, we end up with space group 31. And there's quite a bit of symmetry aspect, constraints aspect that the Lei Chen have a poster tomorrow to describe in some detail. And for the purpose of this talk, I want to use this as an example, the Kondo lattice model again, with strongly correlated F electrons and non-interacting conduction electrons. And this is the 3D version of this particular, the structure for this particular symmetry. And so we solve this model for this Kondo lattice to show that in the absence of Kondo effect, F electrons do their own thing. Conduction electrons live far away, far above the Fermi energy. But once the Kondo effect takes place, we have these composite fermions, which are obliged to live in the vicinity of the Fermi energy within an energy spread of kBtk. And if one looks at in detail, one sees the nodes allow some high symmetry cuts. And if you follow these nodes in detail, one ends up, this model is an inversion symmetry breaking term. So one ends up with these nodal lines. So these are Kondo-driven nodal line semi-metal, and the symmetry allows us to understand why, if the space group symmetry constraints is operating on the composite fermions, we can understand this. So this provides some motivation to think about materials. As I said, this model, the solution here is for a particular filling, but because these states have to happen in need of Fermi energy, filling constraint is not very important. So I'm not, in design of materials, I'm going to ignore the filling constraint and just ask the following question. Let me look at materials that space group 129 in practice. I don't do it. Andrei Prokofiev and Silka Pashin did it. Look at the structure database for space group 29. And just for the concreteness, the amount that CR ions are at the site 2C, just as an example. And so the database told us that there's 142 materials that satisfy this requirement. And one can inspect this 142 materials to screen out those which are expected to be good insulators or good metals, sometimes using the data known experimental properties or of stoichiometric and even excluding good superconductors. And that limits us to 39 of these materials. And 39 of these materials, some of them we know we have access to experimental information, others we don't. Of those we have access to experimental information, we look at the specific heat, which tells us whether it's correlated or not. In spite of cerium atoms in the material, it may not be correlated. And look at transport to see whether it's indeed a semi-metal, and look for DFT for the non-F part of the electronic states, just to give the sanity check about symmetry aspects of the degeneracy, etc. So these combinations led us these two materials. Let me just, and we also look at the space group 31 following the same procedure to identify the third material. So we claim that we expanded the material space by 300%, or at least the candidate level. But the point is that we don't have to restrict to, so that maybe 2 or 3 minutes. We don't have to restrict ourselves for cerium ions to be at 2C sites. Could it be other sites? We don't have to restrict ourselves to cerium atoms. Could it be ytterbium, and could it be uranium, could it be other rare earth and actinide elements? And of course, there are many other space groups. So we feel we make the proposition that this is a flow chart, the procedure that would allow us to identify materials. So far, we've only done this and 31, but it's a well-defined procedure that we're proposing. So maybe I'll spend 1.5 minutes just to talk about further generalizations. Now, I already mentioned that strong correlations drive emerging low energy excitations. The idea is that symmetry constraints also act on this. One can formally justify it in terms of symmetry constraints on the single particle Green's functions. But let me not get into that. Instead, raise the question, what would happen to the symmetry constraints and to the topology if or when non-ferromagnetic excitations emerge at low energies, right? So correlations, we know, doesn't have to produce a heavy quasi-particle, heavy fermion state. It could fractionalize, etc. Does space group symmetry constraint operate and produce useful informations? And so far, we know fractional quantum Hall as correlation-driven insulating state that generally have no free electron counterpart. So we want to look for the gapless analog, and we've set this kind of idea and think about orbitals. If you think about, I'll skip the details. If you think about orbitals, you can start to identify materials candidates for two-channel Kondo effect. And two-channel Kondo effect can generate non-ferromagnetic low energy excitations, and we showed in this work of Hao-Yu Hu that we can indeed find Weyl and Dirac nodes associated with these non-ferromagnetic excitations. And we have several different ways to show that the state we realized is topological. So let me just close by saying that through the thinking about the Kondo effect and degeneracies, the Weyl Kondo semi-metal, which has had quite extensive interplay with the experimental work of CO3 bismuth for palladium-3, venturing further to think about design of this kind of gapless topological correlated phases and materials, and start to think about maybe closing the circle, going back to non-ferromagnetic physics, but with the topological twist. Thank you. There's a question.
So I'd like to inquire a little bit more into your new rules for finding Kondo topological materials. So first, and this is just 2 questions. But the first part is, how strong do the correlations have to be? Is there a general sense for this? And the second part is if you're going beyond cerium, or let's say 1F or 1 hole, whatever, are you thinking that you could go into the middle of the rare earths and actually find things there?
Yeah, so good questions, Nick. On the first part, a priori, in a strong, ironically, in a strong, extreme strong correlation limit, such as a Kondo limit, we have a lot of intuitions and methodology. In the intermediate correlation regime, theoretically, it's much harder to study. But the general principle of having the space group constraints on emerging excitations, and we know even in intermediate correlations, interaction will produce low energy excitations that could be quite distinct from the bare electron excitations. We expect that to work. I don't have a model to show you, but the expectation is that I don't have to restrict to our expectation of 100 or so of materials we can expect. In the Kondo limit, in the intermediate correlation, there should be a room for this, applying this kind of considerations. And the second question was, do I have to think about 1F electron or 1F hole like in cerium and ytterbium cases? No, you don't have to, because in fact, when we start to think about this problem, two-channel Kondo lattice, we've done similar things of searching through materials. And in fact, the praseodymium-based ones with two electrons, the F orbitals are the most natural ones for good reasons. So in this work, we listed several candidate materials just in the category that you asked for.
So when you're talking about the space group symmetry constraint, so do you consider them before adding the interactions or after you got ground state and excitations? So because the many symmetries, spatial symmetries can be spontaneously broken, or they can spontaneously reduced. Therefore, the symmetry, space group symmetry can be changed.
Yeah, so I will stick to the simplest case when it's paramagnetic, etc. Interactions don't break symmetry. I can look at the cases when interactions have broken the symmetry, time reversal or other symmetries, but let me just stick to the simplest case. Right? I think there are several different ways of thinking about your question. One way of thinking about is at which level space group symmetry is operating. So, for instance, degeneracies, right? So when we have this Weyl Kondo semimetal solutions, there's a popular way of looking at the results by saying that, oh, these composite fermions are just inheriting the topology of the bare conductor electrons. In fact, that's not the right way to think about this, because what the interaction needs to do first is to produce these excitations. And then they act, the symmetry constraints act on these emerging excitations. So formally, it's much easier to think about, you have a particular property of the many-body solution, the single particle Green's function of this many-body interacting problem acts in a particular way. So I can introduce eigenvectors and eigenfunctions. The eigenfunction is the spectral function of the eigenvectors. Even though it's an interacting problem, I can analyze the symmetry constraints much in parallel to what one would do to the block functions of non-interacting systems. But the objects are the low energy excitations driven by interaction. So I'm asking that at least this way of thinking, this symmetry constraints acting on these low energy excitations. That's also why we can go to the non-Fermi liquid case.
I'm going to get you covered first, but let's do one last question.
Yeah, the non-Fermi liquid case is, potentially I could imagine many different meanings of the notion of electron topology in a non-Fermi liquid.
Yeah.
So which meaning do you give?
So good question, Anto. At the moment, we are addressing this question. So for instance, we found the state, I can tell you what the spectral function looks like, etc. But what is it? Why do I know it's topological? Right. So we looked at several things. First of all, are there some surface states?
Yeah.
So for instance, this solution I'm showing you is actually the dispersion, degeneracy is actually the analog of wire nodes for non-ferromagnetic extensions. And I don't have a plot here, but there's a plot of the surface states, some kind of drum head states. And so that's one way, surface bulk correspondence, even for non-interacting settings. The other thing we did was to look at various kind of Hall responses, the vary Hall, the spin Hall in the 2D case, etc., to show that they are there, and they are large, they have unusual temperature dependence, etc. So that's another corroborating feature that characterizes the topology of it. And the spontaneous Hall frequency we can also calculate, which we did, and with unusual temperature dependencies. So that's as much as we've done so far. There may be probably a sharper definition to further to come along. But the first thing I want to know is that in what sense this stays topological. And I think perhaps it's along the same direction we are asking.
Okay, so let's thank you again. And we have we have a talk, and then we have a discussion. So please, everybody, participate in the discussion.